Hello everyone, I am Shweta, MSc at Physics from RAE Mysore. So this video is about liquid layers and somatic crystals. We'll be seeing about the properties and dynamics of liquid layers in somatic phases and explore their significance in various scientific and technological applications. Unlike solids, liquids, and gases, these liquid crystals they exhibit fluid-like properties and crystalline properties. So among the different types of liquid crystal, these somatic liquid crystals they stand out because of their distinct layered structure. Here you can see within the state molecules are ordered in liquid crystal, but they possess the mobility of liquids. These somatic liquid crystal comprises molecular layers. So these are the molecular layers. These layered arrangement sets them apart from other liquid crystal phases and plays a pivotal role in their behavior and functionality. This somatic is derived from a Greek word somatikos, which means that which can be washed away. Before going into the liquid layers in somatic liquid crystals, we'll see about some of the somatic phases. So these somatic liquid crystals, they share similarity with conventional solid crystal. They exhibit long range order, so it is also called as long range positional order, and they are mostly one dimensional positional orders and they are within the layers. So the mass centers of this molecule exhibit fluid like behavior. So these somatic phases are subdivided into several phases depending on this orientational. So this has this long range order. So based on this orientational order, they are divided into several phases. Let us see some of the somatic phases. So the first one is called as somatic A phases. Here you can see these molecules are aligned along the normal of the layer of the surface. So this type is called as somatic A. So when you see somatic C, they exhibit uniform tilting. So their molecular axis is not perpendicular to the normal, so that the phase has biaxial symmetry. Coming to the liquid layers in somatic liquid crystal. So before going into what, we'll see about first what are these liquid layers in somatic liquid crystal. So these refers to the individual planes of sheet which are arranged parallel to each other within the material. These layers they possess high degree of molecular ordering while retaining the ability to flow. So we have already seen that liquid crystal have the ability to flow. So here we'll see their distinctive features. So defining characteristics. These liquid layers are a defining characteristics of somatic phases which distinguish them from other liquid phases such as nematic or cholesteric. So now we are studying about somatic liquid crystals. So because of these liquid layers, they are distinct from nematic and cholesteric crystal liquid crystals. So one more thing is ordered structure. So unlike this isotropic liquids where molecules have no preferred orientation, these are arranged in a ordered manner. So these molecules are arranged in orientation. We saw already about the orientational order. So we'll see about their importance. So the first one is structural basis. Liquid layers serve as the structural basis of somatic phases, providing a framework for understanding their properties and behavior. The properties and behavior are further discussed. So coming to the function relevance. These function relevance is nothing but the presence of these liquid layers which influence the material's properties. So what are the properties it is affecting? It is affecting its physical property, optical property and electrical property. So once these properties are varied, they make them more essential for so many applications. Coming to molecular ordering. So we saw they are arranged in a order. So we'll see about molecular ordering. What is molecular ordering? This because of this molecular ordering, we can see that it governs the anisotropic properties of the somatic liquid crystal. Means what? What is this anisotropics? It means the material properties will be varying depending on the direction of measurement related to the layers. We'll see more about this anisotropicity later in the slides. So next one is changes in this molecular orientation. So once this molecular orientation changes, we already saw its properties are also changing. So as its properties change, their functionalities also changes. So as these changes, these are used widely in various applications. Now coming to layer specific orientation. So as you can see in semantic A phases, the molecules are oriented perpendicular to the layer planes, and semantic C, they are almost tilted to an angle relative to the layers. So from these two images, I think the layers of the molecules arranged are visible. So as you can see in the first image, they are arranged perpendicular to each other. So the first image represents somatic A phase, and the second one you can see all the molecules are tilted in the same direction. So this second image refers to somatic C phases. Coming to role of this molecular ordering in liquid crystal, how it is going to affect its behavior. So when you come to ordering, see this is happening within the layers. This molecule ordering, the molecules are ordered within the layers, right? So what is happening? They influence the material's response to external stimuli. So before we saw what properties are changing: electrical, optical, mechanical properties are changing. So based on the change in the property, the material will respond to external stimuli in a different way, such as temperature, pressure, and electromagnetic fields. So this change in orientation, yeah, how it is, why, because of what it is resulting, because its properties are changing. What are the properties? Optical properties, electrical properties, and mechanical properties. We'll see about these properties later in the slides. Now, dynamic interaction. These structured arrangement of the molecules within the layers. So, as we all know, the molecules are arranged and they are ordered within the layers. So, everything is happening within the layer. What is happening now? These layers, these arrangement, it facilitates dynamic interaction among neighboring molecules. So this dynamic behavior underpins the material's ability to respond to external stimuli and adapt to changing environmental conditions. So based on this arrangement, if we change the arrangement, its response to the stimuli will be changed. Why? Because of the material's optical, electrical, and mechanical properties. So based on these properties, they have wider functionalities. So as the properties change, their functionality also changes. Coming to anisotropic. What is anisotropy? What does it mean? It refers to the property of material exhibiting different characteristics when measured in different direction. So as you can see here, whatever direction you measure, if you measure in this direction, you will get one property. If you measure in this direction, it will get different property. So what is the opposite of anisotropy? It's isotropy. Isotropic materials, what they do have, when we measure along all the direction or any direction, the properties remain unchanged. That is isotropic. So here this liquid crystal, what property do they undergo? They undergo anisotropy. Means the property of the material is changing when measured in different direction. So what are the properties which we saw before? We saw optical property, electrical property, and mechanical property. So we'll see what changes are taking place and what are the characteristics of these anisotropic properties. So the semantic liquid crystal exhibits optical birefringence where the refractive index varies depending on the direction of light. So see, depends on the direction. So anisotropicity relative to the molecular orientation within the layers. So this is called as optical anisotropy. So coming to electrical anisotropy. Here the conductivity changes. What happens in optical? The refractive index changes. But when you come to electrical anisotropy, the conductivity of the schematic liquid crystal varies. How? It depends on direction. What direction? Direction of current flow relative to the molecular orientation within the layers. So everything is dependent on the molecular orientation within the layers. So coming to mechanical anisotropy. This schematic liquid crystal display mechanical properties such as elasticity and viscosity that differ how depending on direction of stress or shear relative to the molecular orientation within the layer. So what did we see? We saw what is anisotropy and optical anisotropy, electrical anisotropy, mechanical anisotropy. What is happening in optical anisotropy? The refractive index is changing when we change the direction of light propagation. And in electrical, the conductivity is changing depending on the direction of current flow. In mechanical properties are changing depending on the direction of stress or shear. Now we saw liquid crystal previously, they follow fluid-like behavior. So they exhibit fluid properties as well as crystalline properties. Now we'll see the fluid-like behavior. Fluid-like mobility. Molecules within these liquid layers exhibit fluid-like mobility, allowing them to slide past each other while maintaining their position and orientation order. Yes, this fluid-like materials is nothing but it is going to move, it is going to flow, but their order, their orientational order is not going to change. So they are going to maintain this positional and orientational order, because once this positional and order is changing, what is happening? Their properties will change. Their properties will change, their functionalities will change. So they are going to maintain these and they are going to exhibit, they are going to flow like a fluid. So these dynamic behavior contributes the material's ability to flow and deform in response to the external stimuli. Now, in contrast with the ordered structure which are observed in crystalline solids, so they exhibit two properties. One is the fluid properties, one more is crystalline properties. So this property to flow like a fluid is in contrast with crystalline solids. Now we'll see these behaviors in detail. The first one is dynamic molecular motion. So what is happening here? Despite the arrangement, so these molecules are arranged within the layers. So despite this, these molecules also possess significant freedom of movement within the plane of the layer. So what is happening in dynamic molecular motion? Despite the order arrangement within the layers, they cannot move within into layers to layers, they cannot move, but they have freedom of movement within the plane of the layer. Next one is temperature sensitivity. So these changes in temperature, what is happening? It is going to affect mobility and ordering of molecules within the liquid layers. These schematic liquid layer crystals exhibit temperature dependent phase transition. So when temperature changes, the transition occurs, which leads to alterations in the fluid-like behavior. Next one is pressure effects. When external pressure, they are influencing the spacing between the liquid layers. So what is happening? Again, the mobility is changing here. This pressure induced changes in this molecular ordering, it is impacting the material's viscosity and flow properties. These viscosity and all we saw under mechanical properties. Now coming to electrical and magnetic fields. Application of electric or magnetic fields can induce reorientation. So we saw the molecules are oriented within the layers. So depending on the electric and magnetic field, they are external fields. So once these fields are applied, what is happening? The orientation are changing. So it is getting reoriented where within the liquid layers. So the reorientation is happening within the liquid layers. Next comes role of interaction. Here what is happening? The molecular interaction within the liquid layers governs the material's fluid-like behavior. They have this weak intermolecular forces which allow molecules to slide past each other. So it has the ability to flow without changing its properties. Okay, now the next one, interlayer spacing. So we saw the molecules are layered. Now we are going to understand about the interlayer spacing. So somatic liquid crystal exhibit a distinct layered structure with molecular arrangements in plane or in layers. So that is what is happening. Now what is meant by this interlayer spacing? The space between the adjacent liquid layer. So that is called as interlayer spacing. What? The space between the adjacent liquid layers is called as interlayer spacing. So this is a very critical parameter which is going to affect the material's property and behavior. So now we'll see what are the factors which are influencing interlayer spacing. So temperature, pressure and molecular structure. How the change in temperature, what is happening? It is changing the intermolecular interaction and the molecule ordering within the liquid layers. So now what is happening? When temperature changes, the intermolecular interaction and molecular ordering within the layers are getting affected. So this will affect the interlayer spacing. Next, pressure. What is happening in pressure? The liquid layers are getting compressed or expanded. So now what is happening? The spacing is either reducing or increasing, which leads to the change in the material density and viscosity. Next comes the molecular structure. Here, the chemical structure and size of the molecules determine their packing arrangement within their liquid layers. They influence the interlayer spacing. So this interlayer spacing is nothing but the spacing between the adjacent molecular layer, adjacent liquid layer. What are the factors which are affecting? Temperature, pressure and molecular structure. Next is fluid-like mobility. We saw fluid-like behavior, how they have the ability to flow without changing the position and orientation order. And this dynamic behavior, because of this change, what is happening? They have the ability to flow and deform in response to external stimuli. Next, the interlayer dynamics. We saw interlayer spacing. Now, this interaction between neighboring liquid layers influence the material's overall behavior and response to external condition. The next one is change in this interlayer spacing. We saw how interlayer spacing are changed because of temperature, pressure and molecular ordering. This will impact the material's mechanical, optical and chemical properties, which were discussed in the previous slide. Coming to applications of somatic liquid crystals. They are widely used. How? Because of what? Because since their properties are changing, because of their anisotropicity, they are widely used in various fields. From display technology, optical devices, sensors, drug delivery system, so many. So their unique properties and dynamic responsiveness make them invaluable for advancing technology and addressing complex challenges in modern society. We'll see about liquid crystal displays. So we have heard about LCD, right? So they play a crucial role in LCD, liquid layers. So layers play a crucial role in LCD, where the reorientation of molecules within the layer is exploited. Reorientation is nothing but when will it happen? When it is exposed to some electric or magnetic field, reorientation of the molecules within the layer is happening. So this will control the transmission of light and they create images. So this is what is happening in LCDs. Next, coming to sensors. These liquid layers contribute to the responsiveness of somatic liquid crystal to external stimuli, making them suitable for sensor applications such as temperature sensor, pressure sensor and biosensor. So we saw how temperature, pressure are affecting the interspacing between the layers. Next, photonics. The ordered structure and anisotropic properties of the liquid layers are utilized in photonic application for light modulation, optical switching, and photonic device fabrication. Let us summarize what we have seen in this video. So first we saw about the unique properties. What the liquid crystals exhibit a combination of ordered molecular arrangement, fluid-like mobility, and their responsiveness to external stimuli. So this makes them widely in use in various applications. The next one is structural dynamics. Understanding the dynamics of the liquid layers within the sematic liquid crystals is essential for studying their behavior and properties and guiding them in designing advanced materials and devices. Applications. So we saw they are widely used in display technology, optics, sensing, and drug delivery system. They are owing this because of their unique properties and dynamic responsiveness. Now, current research is happening in multifunctional devices. So they are going to integrate this material with other technologies to develop multifunctional devices with enhanced functionalities and application. So we need a single device which has so many functions. So what are they doing? They are integrating this properties, this materials wide properties and functionalities, and they are used in various applications. The next one is biomedical innovation. Exploring of biomedical application in drug delivery system, tissue engineering, biomedical sensing. They are offering targeted therapeutic intervention and diagnostic capabilities. Coming to environmental monitoring, they are using somatic liquid crystal for environmental sensing. We saw it is used in sensors. So they are using it for environmental sensing and monitoring applications, enabling real-time detection and assessment of environmental parameters for sustainable management practices. So these are the current researches which are ongoing on somatic liquid crystals. Thank you so much. I hope you understood the importance of liquid layers in somatic liquid crystals. Thank you.